Come on, YouTube. Okay, there we go. All right, so we even got that going. Good.
Is that room 247 I see there? Is that...
No, this is Canada.
Oh, you're in Canada. Oh, okay.
Yep. So, yeah, long way away from 247. Technically 210.
Okay.
Hi, Farhad. How are you? You're muted, Farhad. There we go.
Hi, everyone.
Hey Farhad, how are you?
Hi, good, thanks. How are you?
Yeah, not bad.
Good. Hi, Suresh. Oh, I don't see a video of you. Oh, there you are.
Yeah, I usually shut it off.
Oh, yeah, I will, once the thing starts, I'll shut it off. But is everyone healthy and doing well?
Sorry?
Is everyone healthy and doing well?
Yeah, I think so. Everybody's doing well.
And I saw Craig had COVID.
Hey, Farhad.
Well, didn't Craig
Hi,
have
Craig.
before it was cool?
Where are you? I don't see you on the gallery. Oh, there you are. Okay. It's just hi, Terrell. I just have to scroll up or down or whatever, something.
Okay. I think we're still waiting for Eric.
You are okay.
Since he's on the committee.
Hello, Zhuang. I don't see pictures, and Derek. There's some people that I don't recognize.
Yeah, there'll be a decent number of people you don't recognize. So don't worry about that part.
Okay.
Yeah, hi, from Derek Sherman. I'm a former professor of Jonathan's and was glad to join you today, so looking forward to it.
Oh, very nice.
Hey, Jason.
Yep.
Do you have Eric's phone number? Could you?
Oh, I do. Yeah, I'll give him a call.
Ping him?
He wasn't in his office today. So let's see. Yeah, I'll give him a call.
Isn't defense spelled with a S instead of a C?
Well, it depends on the country you're in, really.
Yeah, this is when you have to put your sword down. That's the spelling of defense, as in fencing.
Okay, Eric had a problem with his computer and he's rebooting it, and he said it'll take about 30 seconds, and he hopes
Okay.
by then.
Okay, because if he's having trouble with Zoom, I do have a YouTube link for him if we need to.
He should also be able to dial in with a phone, I guess, if you send the slides, right?
There's Eric.
Great. Okay, so on behalf of Craig Douglas and myself, we're co-supervisors of Jonathan. Thank you all for showing up, and what we'll do is Jonathan's going to give a presentation of the two different parts of his dissertation. After the first part, he'll have time for questions from the audience, and then we'll move on to the second part. Again, have some time for questions for the audience, and then at some point in time, we'll leave them just to the committee to ask them some further questions. So, Jonathan, go ahead and start.
All right. So thank you everybody for attending. So HBO's Game of Thrones is a very popular television show based upon George R.R. Martin's book series, A Song of Fire and Ice. And what's kind of convenient is that the show is so popular that it spawned a lot of interest mathematically in some topics that relate actually very nicely to the problems I'm going to discuss today. So one problem that somebody was interested in was going and identifying some of the major characters throughout the series. And what they did was make use of community network detection algorithms, and those apply very nicely with spectral graph theory, which is going to be the first environment that I'm going to talk about. And then, because the show's had kind of a lot of twists and turns throughout its lifespan, there have been interest in doing projection on what's going to happen in the book series and also the TV series. So there was one author who was interested in projecting whether or not characters would make it through the 6th and 7th books based upon their character arc through the first 5 books in the series. So projecting whether or not maybe Jon Snow would get to the end of the series. And then there were also a group of students at the Technical University in Munich who wanted to make various predictions about the Game of Thrones show. So one that they did was predict which characters would make it to the very end. And another algorithm that they used was very instrumental in projecting that Jon Snow would actually be resurrected. So while they got that projection right, the character that they projected to survive to the very end, Daenerys, didn't actually make it to the very end. And the second problem I'm going to talk about relates, interestingly, to that in the idea of machine learning and also making projections. Okay, so the first problem that we're going to talk about is in spectral graph theory. So with this, we're going to have graphs which are defined kind of as normal. So we have a set of vertices, which are indicated here with all these numbered circles, and edges which connect pairs of vertices. One object I'm going to make extensive use of is what's referred to as a path. So a path is just a sequence of vertices such that each of the vertices in the sequence are distinct, and there's an edge between consecutive vertices. So let's see. So in this case, we can have 1, 3, and 7 as a path. Also 4, 2, 1, 3, 7 is another path. The diameter is a graph invariant that's really fundamental to a lot of the constructs that I use. The diameter is simply the farthest apart that any of the vertices could be. Is a simple way of looking at it. So in this case, you could have to take 4 steps to go from vertex 4 to 7, so pass it through 4 different edges. So for this graph, we would say that the diameter is 4. Particularly, I'm going to focus on special classes of graphs known as trees. Trees are graphs in which you can get from every vertex to every other vertex exactly one way. So in this case, there's one path connecting 4 and 7, and in fact, there's one path connecting every pair of vertices. Okay, I'm also going to want to take advantage of what are referred to as subtrees, and I'm going to use a couple of different notations for different kinds of subtrees. So what I've done here is I've taken the tree from before, and I've just taken vertices 2, 4, and 5, and if I'm going to use that kind of notation, I'm going to indicate with hard brackets around the vertices used. If I want to exclude a set of vertices, so this one I've taken the tree that I started with and excluded vertices 2, 4, and 5, in that case I'll use soft parentheses like this. Now the relation between graph theory and linear algebra and matrices can be done by talking about matrix patterns. So in this case, what we can do is we can create a matrix A, which we'll say has the pattern of T. So in this case, we'll have a diagonal which can have either zeros or non-zero entries, and then we have off-diagonal entries that, when they correspond to the edges, have to be non-zero, and we'll also make sure that the matrix is required to be symmetric. And any non-edges in this tree are going to be denoted with zeros. So here, for example, there's an edge between vertex 1 and 2, so there's going to be a non-zero entry there. There's an edge between 1 and 3, so there's a non-zero there, but there's no edge between 1 and 4, so there's a 0 entry there. So for example, this matrix A in particular would be something that we would say has the pattern of T. So we have a mixture of zeros and non-zeros along the main diagonal, and then we have non-zero entries in all of the entries corresponding to edges. And again, everything is set up so that our matrix is symmetrical. And we can define this set of all matrices that have the pattern of T as a set of weightings, which we'll use with a script S. So it's just all of the matrices whose graph is given by some given graph. Now, for any given matrix, we can talk about the characteristic polynomial for a matrix, which is just defined to be the determinant of x times the identity matrix minus the matrix A in question. And any root for this characteristic polynomial is going to be an eigenvalue for this matrix. And for any matrix, we can talk about the entire collection of these eigenvalues, and we'll refer to that as the spectrum of the matrix, denoted by this sigma of A. Okay, so going back to that matrix from a moment ago, we can easily find that the characteristic polynomial of A is given by x squared times the quantity x minus 1 squared plus this, or times this cubic polynomial. And we can find that the set of eigenvalues is going to be a 0, which is coming from the x squared, 1, which is coming from the x minus 1, and then these three other eigenvalues that I've rounded off coming from this cubic particle. And the graph invariant that I'm most interested in is what's going to be called Q, so the number of distinct eigenvalues. So in this case, we would say that our matrix has 5 distinct eigenvalues, so Q for this matrix would be 5. And overall, I'm interested in taking a tree and looking at the minimum over all possible weightings of the smallest number of eigenvalues over every possible weighting. Okay, so the major question to investigate is, for some given tree, is it possible to go and come up with the smallest number of distinct eigenvalues for that tree in what we could refer to as an optimal weighting? And other kind of sub-questions that we could ask is, if you can't find Q of T exactly, could we at least bound it? And maybe could we find Q of T for particular families of trees? Or again, maybe if we can't find it exactly, could we bound it? Okay, so a couple of fundamental results I take use of. So one is that if your tree is a path on of length n, so n edges, then Q of T is always going to be n plus 1, or in other words, the number of vertices in that path. And then one result that traces back to Cauchy is if you're given a symmetric matrix, A and then also B, if you go and you remove the vertex, or the row and column, the first row and the column, and you go and you order out all of the eigenvalues, what you wind up with is the smallest eigenvalue of A is less than or equal to the smallest eigenvalue of B, which is less than or equal to the second smallest eigenvalue of A, and so on. So whenever we delete a row or column, we get this kind of setup. Okay, so some things that we already know about Q. So the first is that for any tree, Q of T is always at least the diameter plus 1, and that more or less comes from the result from a moment ago. Then in 2002, it was conjectured that it's going to always be the case that for every tree, you can always come up with a weighting so that the minimum number of eigenvalues is the diameter plus 1, but then 2 years later, this was shown to be false, as a tree with diameter 6 was constructed, but you could only get Q to be 8. So for any weighting you picked, you would always have at least 8 distinct eigenvalues. And then our very own Brian Shader, in collaboration with N.J. Kim, went and came up with an infinite family of trees so that Q of T was at least 9/8 the diameter plus 1/2 for every tree in its family. Okay, so Q also shows up kind of nicely in some areas. So one that's really important is that if Q of a graph, so not necessarily a tree, but a graph in general, is 2, that means that there is an orthogonal matrix that has the pattern of the given graph. And then Q is one graph invariant, and there are a couple of relations between Q and other graph invariants. So one is the minimum rank for the graph. So same kind of idea as with Q, so distinct eigenvalues, but for minimum rank, it's just the smallest rank that a matrix in your weighting set has to have. And this one can kind of be seen pretty simply. So the idea with this one is, if you have q distinct eigenvalues, at least q minus one of them are non-zero. And if q minus one of them are non-zero, then that's going to give you a bound on the minimum rank. And then also, q is bounded above by twice the chromatic number of the complementary graph. So the graph complement you could just think of as all of the edges of the switch. So if you start with the graph G, all of the edges in G bar are not edges in G. And the reverse is also true. The edges in G bar are not edges in G. Okay, so the major contributions that I've come up with here. One is that I expand upon what's known as branch duplication, which is what I'm going to refer to in a moment, and I go and introduce two new techniques that we'll see the usefulness of, which I call pruning and grafting. And then in particular, I go in and study the family of ternary trees and go and introduce those into the literature as something else new that's been studied. Third topic that I'm probably not going to touch on very much, if at all, is dealing with symmetry and how symmetry can be used to bound Q for various different trees. Okay, so the idea of branch duplication. So let's just go and start with a path on 5 vertices, which I've labeled as 1, 2, 3, 4, and 5. And I'm going to take A to be the matrix that has the pattern of this path T given as follows. So the first row and column is corresponding to vertex 1, the second row and column is corresponding to vertex 2, and so on. And here we can see pretty simply is that the characteristic polynomial for this matrix is going to be x times x minus 1 times this cubic polynomial. And what I'm going to do is I'm going to duplicate this branch at 2, so I'm going to duplicate the vertex 4 at 2, and I'm going to duplicate the vertex 5 at 3. Okay, so that gives me this new tree, slightly bigger, where I now have 7 vertices. So I duplicate 4 to get vertex 6, I duplicate 5 to get vertex 7, and I'm going to define the matrix A prime to have the pattern of this new tree T prime defined as follows, where these entries C1, C2, C3, C4 are subject to this condition. So the sum of squares for C1 and C2, and then also C3 and C4 is going to be 2. In effect, what I've done is I've gone and taken the one block that we originally had corresponding to vertex 4, and I've duplicated it while shifting the sum of the squares of the entries between C1 and C2. And when we do this, it turns out that the characteristic polynomial is quite nice to describe. We duplicated the block 4, which had the eigenvalue of 0, and we duplicated the block at 5, which had an eigenvalue of 1. And what we wind up with for a characteristic polynomial of this new matrix is just the characteristic polynomial of the block corresponding to 4 times the block corresponding to 5 times the original characteristic polynomial. And this result is formalized by a result from Johnson and Saigo, which says kind of exactly what we've just constructed. But what's kind of, I guess, suggestive in the way that this construction was done is maybe instead of going and building up from one tree to a bigger tree, we could in a sense go backwards. So we could take the same block and we could shift the weighting from a collection of edges onto one. And that's where this idea that I came up with for branch pruning case. So suppose that we have some matrix given like this, but we have these two blocks here that are identical. So we have this block B, and also B is corresponding to two different parts in the matrix and also the graph. And I have these entries that are connected to B. So I have B1 times just the vector with a 1 in the first position, zeros and all of the rest. And then I have B2 times the same vector. As it turns out, what we can do is we can look at a slightly different matrix, A prime, which is the same in the top left and almost the same everywhere else, except we've gone and made the sum of squares, we've shifted it all onto one edge. And when you do this, it turns out that the characteristic polynomial of these two matrices is the exact same. So in other words, what we've done is, graphically speaking, we'll see that we disconnected one of these copies of B. Okay, so how does this work? Well, suppose I have this tree. What I could do is say, I'm going to assign the same value to this block 2 and block 3. I'm going to assign the same value to blocks 5 and 6. And I'm going to assign the same values to 8, 9, 10, and 11. 11. And that would allow me to go and disconnect some of these vertices. So I'd be able to go and shift all of the weight from the pair of edges that were here just onto the edge between 1 and 2, which has the effect of disconnecting vertex 3. And I'd have the same thing at 6 and 9, 10, and 11 as well. The next thing that I could do is, suppose that I originally set things up so that now the block 1, 2 has the same, is the exact same as the block 4, 5, which is the same as 7, 8, 12, 13, and 14, 15. We could have done this pretty simply by from here saying, I'm going to assign these two edges to have 1 over square root of 2, these will have 1 over square root of 2, and these ones will have 1 over 2. That way the sum of squares for all of these would be 1. And then when I would do this, I would just go and say, let's make all of the diagonal entries 0, so that way I would get these blocks to all be the same. And then I'll also go and say put zeros at 16 and 17. And when I do that, that would mean I'm able to go and shift all of the weight that was on the 0, 14 edge, 0, 12, 0, 7, 0, 4, 0, 1, and shift it all into just this 0, 1 edge, which again has the effect of disconnecting more of these entries in the matrix. Okay, and this method works really, really well when the matrix blocks are the exact same, but that's not always going to be the case. So then that motivated me to come up with this idea of grafting. So what grafting says is, let's go and take a tree that kind of looks like this. So I have some vertex V, it's got a branch over here, B1, it's got some more of these trees over here, all the way over to BK. And then I have these paths down below. So I have P1, P2, all over to Pn. What we can do is we can go and use the same kind of idea, but slightly different, to go and shift all of the weight away from the edges connecting V to P2, V to Pn. We can shift things over to P1, subject to a couple of nice conditions. So one is that the matrix corresponding to this weighting will have the same characteristic polynomial as the matrix corresponding to this tree. And then also Q1 is going to have as its spectrum the union of the spectrum for the blocks corresponding to P1, P2, all the way over to Pn. And then Q2 we can define to have as its spectrum all of the eigenvalues that are in at least 2 of these paths, and then all the way over to Qn, which will have as its spectrum every eigenvalue that is in every of these n paths. Okay, so a couple of implications that follow really quickly from this that apply really nicely in the case where we're looking at weightings that have the diameter plus 1 bound. So one is that if you're going to have diameter plus 1 and there's a diametrical path, so in other words a longest possible path, that's going to go through, we'll say P1, then it has to be the case that P2, that all the eigenvalues in P2 are also eigenvalues of P1, and the same holds true for all of these paths. So every other path, P2, P3, all the way up to Pn, they all have to have the same, or there can't be any new eigenvalues introduced. The reason for that is kind of straightforward, because when we go and we shift from P1 to Q1, if there was an eigenvalue, say, in P2 that was not in P1, this path Q1 would get at least 1 longer. And if there's a diametrical path that went through P1, I'd be going and increasing the length of this path, which would go and increase the diameter. And because the diameter plus 1 is always a lower bound on Q, I'd wind up saying that I couldn't actually get this diameter. I'd wind up with a new diameter plus 1, which is 1 bigger than the original one. Okay, another result that is kind of in the same vein is saying, if I go and take a diametrical path and I remove all of the vertices on that diametrical path, every eigenvalue that appears in the graph in the tree or collection of trees that remains has to be an eigenvalue of the entire matrix. And this is going to kind of follow from the same reason. Okay, so what we can do is we can use these ideas of grafting and also pruning in looking at what are called ternary trees. So a ternary tree is going to be defined as a tree in which every non-pendant So a pendant would be something down at the very end of the tree. So a non-pendant has degree 3, and nicely up to isomorphism, there's going to be exactly one ternary tree for each natural number. And we'll denote this by a Tm. So for example, here we have the ternary tree T6. So what we can see is that every non-pendant has degree exactly 3, and then we have pendants down here, 18, 19, 20, 21, and so on. Okay, and then what we can show is that for at least m equals 3, the ternary tree T2m is not going to meet this diameter plus 1 lower bound. In fact, you're going to have at least diameter of your ternary tree plus 2. Okay, so what I'm going to do with this is I'm going to kind of sketch the proof using T6, and the construction that's going to be used on T6 generalizes to T2m for m bigger than or equal to 3. So what I'm going to do is I'm going to focus on this vertex 11. And I'm going to go and take diametrical paths that are going to go and cut off components that include vertex 11 that I'm going to focus on. So the first one is I'm going to take this blue diametrical path, and it's going to leave vertex 11. Then I'm going to go and take another diametrical path, which is going to leave this component containing also vertex 11. And then lastly, I'm going to take a third diametrical path that is going to include another component containing vertex 11. And then what we're going to do is we're going to go and rely on one of the results that we just had. So whenever you remove a diametrical path, every eigenvalue that shows up has to be an eigenvalue of the matrix you started with. So for example, the eigenvalue corresponding to vertex 11 has to be an eigenvalue of any weighting you come up with. The 3 eigenvalues in this block, 4, 10, and 11, they all have to be eigenvalues of the original matrix. And the 7 eigenvalues corresponding to this component also have to be eigenvalues of the original. Now there's also this result from Johnson and Saigo that says that the biggest and smallest eigenvalues for a tree will have multiplicity 1, and they also cannot be eigenvalues of any subtree. So for example, we would have the eigenvalues of this entire tree have multiplicity 1, and if I'm going to come up with a weighting for this tree that has this diameter plus 1 lower bound, or has exactly this diameter plus 1, I'm only allowed 7 eigenvalues. So here I would have my biggest and smallest, that's 2. They're not allowed to be eigenvalues of a smaller tree. I have the eigenvalues of this entire block, so this component of 7 vertices, I have biggest and smallest for those are 2 more. Going back here, I would have the biggest and smallest eigenvalues of this 4, 10, and 11 block. They cannot be eigenvalues that we've seen before, so that's 2 more. And then I have that eigenvalue corresponding to vertex 11. So that's my 7 allowed eigenvalues. And what we could do is we could say, well, there's nothing really special about vertex 11. We could have gone and started this from any other vertex, and we'd get the same kind of result. We would get these same 7 eigenvalues that have to show up. So what that's going to tell me is that the blocks 10 and 11 have to be the exact same, which means I could apply the pruning theorem there, shift the weight that was on the 410 edge and 411 edge just all to be on the 411 edge. And then I can do the same thing at every other vertex here. Well, recursively what we're able to do is keep applying this pruning theorem by arguing that every of these corresponding blocks has to be the exact same as effectively the block beside it. So this 512 block has to be the exact same as this 411 block. So we apply the pruning theorem, and we get down to this collection of paths like this. And the way that everything has been set up, this path 2, 6, 15, the eigenvalues from there are not going to be eigenvalues of this 0, 1, 4, 11 path. So that's 7 eigenvalues accounted for there. Those will have to be the 7 eigenvalues that we've already seen. But also this 7, 16 path, the eigenvalues there are not going to be eigenvalues in 2, 6, 15, which means that if there is a matrix that has the original ternary tree T6 as its graph, and also 7 eigenvalues, the 2 eigenvalues in 7 and 16 have to be eigenvalues of 0, 1, 4, and 11 path. But it's somewhat straightforward to show that this can never...
What's the matter, George?
So it's fairly straightforward to show that the two eigenvalues from 7 and 16 cannot actually be eigenvalues in this path from 0 to 11, which would mean that I've got 4 eigenvalues from this path, I've got 3 more eigenvalues from this path, and at least one eigenvalue between 7 and 16 that isn't accounted for in the 7 that we had from before, and that will go and force at least 8 eigenvalues for any weighting of the ternary tree T6. And again, we can go and take this kind of weighting or this construction and generalize it to an arbitrary T2. Do the exact same thing. It all works very nicely. Okay, so a couple of things that I'd like to look at going forward. So one is find Q of T8. So the result that we just had says that T8 does not achieve the diameter plus 1 lower bound, so it is not possible to come up with a weighting for T8 that has 9 distinct eigenvalues. So it'll take at least 10, but I have a weighting that gives you exactly 11 distinct eigenvalues. So the question that would obviously be raised is it possible to come up with some weighting for T8 that has 10 eigenvalues? And another thing that I would like to look at going forward is taking the pruning and grafting theorems and seeing if they can help at least bound Q for various families of trees. So I've already used these to go and come up with answers for the family of ternary trees, but then I'd also like to look at some of these for other families of trees. Okay, so I think at this point we said we were going to stop and take a couple of questions over this topic. So if anyone has questions on this one, please ask away. Are there any questions from the studio audience? Okay, so then if there are no other questions, then we'll move on to the second topic. There. Okay, so the second problem that I've been looking at is going and looking at making machine learning predictions in the realm of baseball. So baseball is kind of one of the original sports in which there was kind of sizable academic interest in. So one was in predicting which pitch will be thrown next. So this would be something very, very useful if you're in a game. So what the authors did here was they said, well, we're going to look at every pitch that a pitcher threw in 1 year, and then look at the kind of sequence of pitches thrown, and then go and predict how well that, go and see how well that allows us to predict the subsequent pitch we would throw in the next year. We've also got machine learning applied to predicting whether or not an at-bat will end in a strikeout. So 2 different ways of going and applying machine learning to baseball for kind of in-game applications. And then there have been some applications for more outside of games. So you could think about it more as team building. So one was going and trying to find undervalued pitchers. So the idea with that one is you have this collection of pitchers that aren't thought of by the baseball community to do well, but the underlying statistics and numbers and machine learning says, actually, this pitcher will outperform what he's expected by the baseball community to do in the next year. And then on kind of the same notion, predict how a player will perform in the next year or next couple of years based on his current, based on how he's done so far at the major league level. And this is kind of one of the important things, is that any predictions in this realm have mostly dealt with the major league level. And what's really kind of a blank here is there's nothing that is talked about the baseball draft. And in fact, the only application of machine learning that I could find to the baseball draft deals with fantasy baseball. So it has nothing to do with the actual on-field baseball product at all, just internet games, basically. Okay, so the way the baseball draft works is that every high school and collegiate player across the United States and Canada is eligible to be drafted. And also every junior or senior at a 4-year institution across Canada or the US is eligible to be drafted. And there are kind of some intricate rules afterwards, but for the moment that's all we need to focus on. When a team goes and drafts a player and they sign that player, they have exclusive rights to that player for until such time as the player has played 6 years at the major league level. So quite a long time, and then that player also has to matriculate up through the minor league system as well. And what's very nice about this is that baseball players who have been drafted and not eligible for free agency, so until this 6-year time limit has expired, are very cost controlled. So if anyone is familiar with the Brad Pitt and Jonah Hill film Moneyball, this was one of the main ideas, was that Oakland was operating on a very limited budget compared to all the teams they were trying to compete against. For example, the New York Yankees, which have a more or less unlimited budget. And they need to come up with players who would contribute very well at the major league level, but were also not going to cost a lot of money. And one way to do that is by finding a lot of players in the draft, because for this 6-year time window, they're very, very cost controlled. And it also allows you to allocate money, more money elsewhere. So the question I'm focusing on here is, if we only have play-by-play data from a player's collegiate career, can we make reasonable predictions about how well that player is going to do at the major league level? Okay, so the way this works is the NCAA has all of the play-by-play data for all of their games from 2012 through 2020, until the season got cut off by coronavirus. Unfortunately, they have nothing before that. So, while this 8-9 year window, it sounds like a lot of data, it's really not. The main reason for that is that I'm trying to make predictions about how a player's career is going to go based on maybe the first 2-3 years, if I'm lucky, of their major league career. So not a lot of data to actually work on. For each player, I assign variables based on how well that player has performed, how the player's teammates have performed, and also their opponents. So one of the ideas with looking at how a player's teammates perform is that if you have a player who is playing with a lot of other good players, that would probably suggest that you're going to have this collaboration between players, and that's going to be benefiting the player in question. And we also want to see what a player's opponents do, because if a player is getting very good numbers against very weak opponents, maybe those numbers are just a mirage and it's a player who's not very good. Okay, and then I make 4 different kinds of projections. So one is whether or not a player will be a top prospect. So for this, there are companies that produce lists of top prospects, so the 100 best prospects in baseball. By organizations such as Baseball America, what I project here is, will the drafted player ever make a Baseball America top 100 list? Also, I project whether or not a player will ever play in a major league game, and then I make 2 projections based on what is known as wins above replacement. So wins above replacement is a metric that seeks to measure how much a player is contributing to winning, compared against a hypothetical replacement one. So if a player has a negative WAR, wins above replacement, that means the player is actually contributing to losing games. And if you had a hypothetical replacement that you could put in place of this player with negative WAR, you would be better off. If you have a player that has a WAR in between 0 and 1, that's a player that's very easily replaceable by some hypothetical replacement. If you have a player with a WAR between 1 and 2, that's roughly corresponding to a good bench player, maybe a fringe starter. And for a WAR between 2 and 4, that's going to project to a good quality starting player. And anything 4 and above, you start talking about all-stars and MVP caliber talent. So 4 and above is where you really want to go. Unfortunately for me, with the data limitations that I have, there's just not enough data to make projections about players getting 4+. Okay, so the way that I did all of the projections is using a software package called AutoSKLearn. So this is built on the Python library sklearn or scikit-learn. What AutoSKLearn does is it takes what is called an ensemble, so a collection of various methods, and goes and compiles them all into one kind of best case model. So go and kind of take a vote from a wide collection of machine learning techniques and use that to go and return a model. And I'll mention a couple of other benefits for AutoSKLearn in just a moment, but I want to mention first one kind of machine learning technique that AutoSKLearn will use. So when going and doing these kind of projects, we go and we take all of our data and we split it off into what's called a training set, which is used to build the model, and then a test set, which is used to see how well the model is it's been generated. So suppose you have this collection of data that are labeled as diamonds and circles, and you want to separate them so that you can say all of the points in this area are diamonds, all of the points in this other area are circles. Well, what we could do is we could just go and put one line through here, and it'll go and partition all of the diamonds together, all of the circles together, and that works great. We could also go and take this other, this green line, and it'll do the same trick. It'll go and say everything above the line is a diamond, everything below the line is a circle. Right, so we have these 2 different lines that work very well for our test set. And now maybe we start introducing, for our training set, now we introduce some test data. So I have these 2 triangles that we've introduced, one over here which we'd say, yeah, this one's above the lines and it's really close to a diamond, that one should be a diamond. And this one is over here, this is what we could, this one we'd say, yeah, that one's a circle, no problem. Okay, well what if I introduce a triangle right here? Well, it depends on which of the two separators I picked. If I pick the black separator, this triangle is falling below the black line. So we'd say, well, it's a circle. But if you pick the green separator, the triangle is above the green separator. So you would say, well, it's a diamond. Okay, so there's this issue that we run into. Another issue is maybe there is no separator. So in this case, we have diamonds that are in between circles. There's no way of putting a line that's going to separate this data into circles on one side, diamonds on the other. Okay, and this is where what is called a support vector machine, or an SVM, comes in. So what an SVM does is it seeks to separate the data in such a way that you maximize what's called the margin, so the distance from any point to the line. So in this case, what we can see is, yeah, the distance between this purple line and these diamonds is pretty far apart. The distance between the purple line and the circle is also pretty far apart. And here we have is the triangle is just falling above the purple line, so we'd say it's a diamond. But when you do this, what you have is any point that gets too close to the purple line, so too close to the separator, you would say that's a bad point. So you go and assign a penalty score to this point. And while that's good, the problem it introduces is you have choice in how important you want this to be. So you could say, I'm really concerned with having a margin that's very big, so as big as we can. And if you do that, I think you're going to pick you're going to have a parameter that you're going to have to tune. The other way you could do this is say, well, I'm not really that concerned with having the big margin. I just want the classification to work out really well. And in this case, you could pick you could have the parameter be very small so that the margin is also small. And if you do that, what you wind up with is this line that's kind of oscillating with a couple of these diamonds. So if you pick this separator with a small margin, this triangle just fell on the wrong, or maybe not the wrong side, but it fell on the other side. So it fell on the circle side of the separator. And this is where AutoSKLearn also becomes very useful, because it goes and takes care of all this parameter, any of these parameter issues on its own. So it'll go and test various different parameters when it's going and building the model. Okay, so one other part with this that I was interested in doing is saying, well, let's go and look at some players that have been drafted in later rounds. So for example, if players that are drafted in the 9th, 12th, and so on rounds. And these are all players that have developed into very good major league players. And what I'd like to see is, can I at least make models that could project this success? Right, so some players, Mitch Garver last year with Minnesota, he won a Silver Slugger, which is an award for best hitter. He won it as the best hitting catcher in the American League. Mike Yastrzemski, maybe best known for being the grandson of Boston Red Sox legend Carl Yastrzemski, made his major league debut last year with San Francisco, and he hit about 25 home runs in his debut. Brandon Woodruff has been an all-star pitcher for Milwaukee. He was drafted in the 11th round a few years ago. And as it turns out, when going and looking at all of these models, they do project all of these late round successes pretty well. So, for example, with the case of Mike Yastrzemski, it says that he should be regarded as a top prospect, even though Baseball America never acknowledged that he was a top prospect. It says he will make the major leagues. It says he will have a season of at least 1 WAR, and he'll have a season of at least 2 WAR. And for someone drafted in the 11th round, that's quite good. We also see that for most of these players, there are a lot of yeses showing up, a couple of no's. You might also notice that some of these predictions are very contradictory. So for example, John Means is projected to not make the majors, but somehow have a season of at least 1 WAR. The reason for this is that we have different training sets, so we do have slightly different models for each of these. Again, with Jeff McNeely, he's not projected to have a season of 1 WAR, but he is projected to have a season of 2. Same kind of. The different models in play lead to some of these strange contradictions. Okay, so then we can also go and look at how accurate these models are. So I'm going to use 3 different metrics to go and look at go and see how good these models are. So one is the accuracy. The accuracy is measuring how many of the projected successes actually turned out to be successes. The recall says how many of the successes that we observed were projected to be successes. And the MCC stands for the Matthews Correlation Coefficient. And what it measures is how well are the models doing compared to just random guessing. So for the Matthews Correlation Coefficient, a score of 1 means perfect agreement. So all of these successes were projected to be successes. All of the failures were projected to be failures. A score of -1 means perfect disagreement, so all of the successes were projected to be failures, and all of the failures were projected to be successes. And a score of 0 means, if you just told me the size of the successes and failures, you could randomly guess and you'd get the exact same result. So for this, what we see is the accuracy scores are not great. In particular, what we see is that the accuracy for getting a season of 2 war is only about 5.5%. So if I project 1,000 players will be successes, I'm only getting 55 actually turn out to be successes, which doesn't sound great. And for pitchers, the setup is even worse. I'm down at 1.5%. And those numbers seem really bad, but it's worth comparing to how well the professional teams actually do. So I have a table here which is going to say the success rates for all of the teams by various rounds in the draft. So for example, there have been 29 batters taken in the first 5 rounds, in the first 5 picks of the draft from 2005 to 2015, and only 11 of them averaged 2 WAR per season over the course of their careers. Now, I've moved the goalposts a little bit from looking at just one single season to averaging out over the course of a career, but it gives me something to kind of compare against. And for pitchers, the success rate is even worse. So there were 7 pitchers that had at least 2 WAR per season over the course of their careers, out of 26 pitchers taken in the first 5 selections of the draft. So you can imagine that this is the best possible case. You have your pick of the lot for batters or pitchers. The success rate for batters is under 40%. Success rate for pitchers is only about 25%. So if you pick 4 pitchers in the top 5 slots of the draft, you don't suggest that one is going to do anything notable. And as we move down throughout various rounds of the draft, we see that after about the 2nd round, it's a complete crapshoot on whether you're even going to get a competent batter or pitcher. So all of a sudden, that 5.5% success rate that I had really doesn't look that bad. And even for pitchers, that 1.5% success rate, it also doesn't look that bad in comparison to how the professional teams are doing at drafting and developing their players. Because as we have here, the success rates are very low. And for something like this, if you could go and make even a small improvement, so if I could manage to get the success rates up to about 10% for both batters and pitchers, I'd be able to project things really, really well compared to the professional teams. Okay, so a couple of things that I'd like to do with this going forward. One that I kind of mentioned a little bit is data. If it's possible at all, I would like to be able to get data going back further in time. That way I'd be able to go and make better projections based on things seen. If that's not possible, I really can only go and look at things as we go forwards in time. So just continuously accumulate all the data that's available and make these projections as we go forward. The other thing that I'd like to do is go and start applying neural networks to this problem. So neural networks are something that have only very recently shown up in the literature for machine learning and baseball projections. For the most part, neural networks haven't been seen here. And it'd be very interesting to see if neural networks could get me an improvement on the accuracy that I've seen so far. So thank you for attending.
So are there any questions for Jonathan from the audience?
Jonathan, this is Suresh.
Yes.
A few questions on the machine learning, the support vector machine.
Yeah. Could you speak up a little bit?
A few questions on the your machine learning algorithms, what you have developed for the baseball
Yes.
classification.
Yes.
The way we do nowadays in machine learning for classification, we actually predict the probability of a input pattern belonging to a particular class rather than just telling it belongs to this class or that class.
I'm sorry, I can't really understand you.
Okay, Brian, maybe you can, based on my...
No, I mean, I just can't hear your audio very well.
Oh, sorry, okay. Okay, the support vector machines are typically in machine learning nowadays. When you do a classification problem, we just don't tell the class membership of each class. Instead, we give the probability of a particular pattern belonging to a class. So what happens is at the output layer of your support vector machine or even a neural network, what you are planning in future, we use what is called as a softmax layer, which will predict the probability of a input pattern belonging to a particular class.
Okay.
So my question is, why are you just doing a discrete kind of classification?
Okay, so why would I do it just a straight binary? So
Yeah.
probably just the simplest way of doing it is because the data is kind of limited already, and I'm just trying to make, I'm just trying to go and take as much of a question as I can bite off without biting off too much that the data restrictions start kicking in. So for this, as I kind of mentioned, there's only so much data to play with originally, and I just say, well, it's useful to be able to predict whether or not I can just get this binary label of had a season of 2 war versus not. I didn't mention how small some of these success rates are, but there are not very, well, I guess it's kind of clear from this table, there aren't very many players that are even going to fall into these success these success parameters. So for that, it just seemed easier to go and take, well, let's just go and take this binary discrete labeling.
What is your size of your data? How many samples do you have?
How many players are there? If I remember this correctly, there I think about 10,000 of both batters and pitchers, but the number of successes is very small. I think the number of successes for 2 war in a season that I had might have been 30.
Okay, that would mean that your data is actually heavily biased for one.
Oh, yes, heavily biased towards failures. And again, this makes sense because there are going to be, think about how many universities there are across the United States. There are hundreds of universities that are playing baseball. And very few of those players are even going to get to a major league game, and even fewer of those are going to do anything notable. Very few are going to have a notable achievement. So yeah, so that's one of the other issues that kick in is it's heavily biased in favor of the failures.
Okay. If data is heavily biased, then we actually there are other 4 or 5 performance metrics. It is not just saying that it belongs to this class or it's misclassified or classified. So I sent a Word document to Brian. Maybe you should take a look at that.
Okay, sounds good.
Yeah. Okay. That's all I had questions for you.
Okay,
Thanks.
Thank you.
Other questions? Okay, hearing none. Oh, go ahead.
Thank you. Thank you, Jonathan. That was a very good talk. So I would imagine if a baseball player at, let's say, a high school level, could he input some of his stats or data, whatever, or college level into this and say, okay, this is how successful I'm predicted to be, and then use that as some type of resume? Is that possible or no?
So high school data is not really available at all. And even if it was, it would probably be only available at state level. So maybe, so I did try and find this, but I couldn't find anything kind of standardized. But maybe there would be something like California maybe would have something, but I couldn't find any data on high school players. So it wouldn't, it's just not something that I can look at.
So, okay, so just to follow up to that question, so like specifically a player could input his data and say, okay, X, Y, this is, if I did this, did that, and did this, then I could be a professional, like make it to the MLB, right? Is that?
Well, it would maybe project. So remember that it's not just how a player does, it's also the teammates you're playing with, the players you're playing against. But you can say,
true.
hey, I'm going to have these numbers, my teammates will have these numbers, my opponents will have these numbers. Where would I be projected to fall? Yeah, so
Gotcha.
You could definitely do something. You could definitely introduce a hypothetical player into this and project where they would fall. Yeah.
Okay, cool. Thank you.
Yeah, thanks.
Any others? If not, then let's thank Jonathan, and also thank each of you for showing up and listening. And then after we thank, I'll ask you all to log off, and then just the committee will work with him.
Thank you, Jonathan.
Thank you everyone for attending.
Thanks, Jonathan.
Yeah.